Yeah. Pair transport and the covalent derivative. This is what I'm talking about today. Okay. First of all, let's recall the formula we already got. Okay, so this is a surface and have a curve. Okay, and on the surface, we do have the so-called second fundamental form. Okay, then given a curve and view the curve in the this is a normal vector. Okay, so so this is a gamma. Okay, and so it's gamma. Okay, the second derivative. Okay, and that is going to be the normal curvature at the point S, right? It's going to be the second derivative, the projection on the normal vector. Okay. So this is this turns out to be this turns out to be the value of second fundamental form in the direction, in this direction, the tangent direction. And what is second fundamental form? What's the first fundamental? Let's second fundamental form, by definition, right? When you expand, let's go back this. Okay, when you expand, this is a surface, we call surface patch, right? So here's a point in UV, and this is a point P sigma UV. So how do we get a second fundamental form? We basically find the Taylor expansion. Okay, so U plus delta U, V plus delta V. When you expand it, that's the first term, right? The second term gives you a tangent vector. So this is a tangent vector. Okay, then the second fundamental, the second one, right? By Taylor expansion in two variables. That would be sigma UU. Okay, I'm not going to put the variable here, delta U squared, twice of sigma UV, delta U, delta V, sigma VV, delta V squared. Okay, then plus the high order. Okay, the high order, this is delta U squared, delta V squared. Okay. This is Taylor expansion, but this one is a vector. But this vector has two parts. The part, see, in tangent space, right? On this plane, right? You have a normal vector. Then you also have, this plane, right? So this can be decomposed into two parts because of the, this will be something like that, okay? This will be the second order derivative, right? So this is this can have a delta U squared, right? Plus sigma UV, delta U, delta V by sigma VV. This is a vector, right? So this vector can project it to the normal vector, also can project it to the tangent plane. So there'll be two components here. So two components here. And we want to express in two forms, right? So this is actually, how can I express it? This is a vector in three-dimensional space. This can be written in the form gamma 1. I'm going to use gamma 1 here, okay? So sigma U is because this is a tangent part, sigma V. And also the projection onto the normal vector. This turns out to be the second fundamental form. Second fundamental form evaluate at the point, okay? V. What is the V? V is a sigma U delta U, sigma V delta V. Okay, so this is second fundamental form. Okay, by definition, right? The second fundamental form is defined to be the dot product of n with this vector, right? The second fundamental form is defined as the dot product n. Okay, so that is a definition. Okay, we have a DEF means definition. And for that tangent vector, okay, and it's well defined, and we said then you get, it's expressed in using surface patch, and expressed in surface using a surface patch, but it should be independent of surface patch. That's why the left-hand side you don't see the symbol sigma. Okay. Now, in for today's class, we are interested in this part. Okay. We're trying to figure out this part. Okay. Now, this part is a projection of the projection of the vector, this vector, onto the tangent. Okay. And so my notation may be slightly different, but it's clear. We don't we understand the second fundamental very well, right? So we're trying to understand this part. This is not going to be. It probably depends on. Okay, this one, the second fundamental form is an important factor. Is this is independent of the choice of sigma. Okay. However, the tangent part depends on choice of sigma. Okay, that's the first fact. Second fact, gamma 1 sigma u, gamma 2 sigma v. This in general depends on the choice of sigma in general. Okay. So in general, it depends on it depends on the choice of sigma, but it's okay. So the question is, what is a sigma 1, sigma 2? Then how do you find it? Right? How do you find it? So in order to determine, but how does sigma 2, how does that look like? Because sigma 2, we can express in the form like that, right? Okay, we can also express sigma. Okay, so actually, in order to determine sigma 2, you have to determine all those coefficients, right? Why this depends on delta A, delta V? Because this side, look at this expression, right? It depends on delta A. So the UV and delta A, delta V. Okay, so the point is, how do you find the gamma 1, gamma 2? Okay, how to find the gamma 1, gamma 2? To determine gamma 1, gamma 2, all you have to do is the inner product with sigma u and sigma v, I think. Okay, the inner product with sigma u, so the inner product was so this is again the product with sigma u and sigma v. Okay, so then gamma 1, right? Sigma u will be E. Gamma 2, sigma u, sigma v is going to be EF. and the other side will be sigma UU dot U, right? Yeah, this is with sigma U, right? So the right hand side, so sigma U plus sigma VV, sorry, delta U delta V here, and sigma U delta V squared. Okay, and then the same identity, this identity, and the dot product with sigma V. Then sigma U, sigma V is going to be E, right? It's going to be F here, F. Then sigma 2, this will be G. And this side is still same, right? Dot sigma V. Okay. So we were trying to solve gamma 1, gamma 2. Okay. All I have to do is just express this coefficients. Okay, we're going to express this coefficients. Now, how do I express this coefficient? Let's calculate, okay? Sigma UU and dot sigma U. This is half of sigma U dot sigma U, right? So it's half of E, U, right? Partial derivative E with respect to U. And sigma UV dot sigma U. And that will be half of sigma U dot V, V, right? Yes. So this will be, I think, EV, right? Yes. How about the last one? The last one is most difficult. Okay. So first of all, I have to, yeah, then sigma V, sigma UV. Okay, that's the first part. Then I switch the order. Minus sigma V dot sigma V, then U. Okay. So then you can get EF, this is FV, minus half of GU. Okay. So this is the only part. A little bit more complicated. So anyway, those coefficients can be expressed as a partial derivative of the coefficients of first fundamental form. Okay. Then let's look at the second group. Okay, and similarly, this we have trouble here, sigma V and U, right? Then minus sigma U dot sigma V dot U. Okay, so how about this part? This part, half of sigma U dot sigma U V. Okay, it's just in the product rule. So this is the EU minus half of G. No, this is FU. Okay. Minus that's EV. Okay, and the next one is easy. This is just half of sigma V dot sigma V U. Okay, so this is half of GU. And the last one is half of sigma V dot sigma V. So it's half of G. That's it. So all the coefficients on the right hand side are expressed in terms of U. So the left hand side, E, F, F, G, gamma 1, gamma 2. On the right hand side, we do have let me put the details here. Then I'm not going to give you the formula for gamma 1, gamma 2, but you can see that okay, that's the first one. And here's Fu minus EV delta U square and GU delta U delta V plus half of JV delta V square. So those are expressed in terms of the partial derivative of the coefficients of first fundamental form. So this one, you can use the inverse matrix, right? So gamma 1, gamma 2 can be expressed in terms of, so this is remember gamma 1, how do you express gamma 1, gamma 2, right? Yeah, we have the gamma 1, 1, right? Remember gamma 1, 1, right? Delta U squared twice gamma 1, 2, delta U, delta V, blah, 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 right? So my conclusion is gamma 1, 1, gamma 1, 2, 1, gamma 1, 2, 2, gamma 2, 1, 1, gamma 2, 1, 2, gamma 2, 2, 2 can be expressed in terms of E, F, G, and their partial derivatives. All right. So let me repeat again. Sigma UU delta UV square UV and delta U delta V sigma VV delta V square is going to be gamma 1 sigma U gamma 2 sigma V plus the second fundamental form evaluated in the direction of V, and V is a sigma U delta U sigma V delta V. Okay, so this is our identity. Okay. So we determine the first part actually is the tangent part. Completely depends on those coefficient depends on EFG. This is second fundamental form, of course, depends on second fundamental form. So this part, this part, it depends on the first fundamental form. Okay, right? All right, that's great. All right, and that's good information. Okay, now let's look at a vector. Yeah, maybe we can find the remember the geodesic curvature, right? So yes. Yeah, let's see. Okay, so consider curve gamma on the surface. Right? Now you can describe gamma S in the form, here's S is going to be the arc length, right? So it's unit speed, okay, unit speed. Unit speed. So I'm going to find the second fundamental form, a second derivative, because the second derivative gives you two parts. First of all, let's see, I'm going to use the same order as we did. Okay, so the so-called geodesic curvature, the coefficient, NS cross gamma prime S plus the normal curvature NS, right? So this is the normal vector around this. It's a preset. So we already know what is this part, right? This part is just the second fundamental form. Evaluate in that direction. Okay, now how about this part? This part should be the, we don't know, right? Let's do the calculation, okay? So more likely it's determined by gamma 1, gamma 2, okay? Okay, so let's find the first derivative. First derivative is sigma u, right? The second derivative is going to be sigma u, sigma v double prime, and then this switches order product, right? So u prime, sigma u, u prime, sigma u v, v prime, right? And plus v prime, sigma vu, sigma vv, right? So actually, what we get here is, let's write in the form u double prime sigma u, v double prime sigma v, that's a linear part. And then we have sigma u, right? So u prime square plus sigma uv, u prime v prime. This looks like a delta, delta u, delta v, right? Okay, great. But we already did the above decomposition, right? So you replace delta u by u prime, delta v by v prime, okay? So what do we get? This is a part gives me gamma 1, right? Sigma u, gamma 2 sigma v, and blah, 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 this n, right? Okay. So, so here v is going to be the direction. So just the second fundamental form. Yeah, okay. I don't, for the simplicity, I don't put the S here. Okay. All right, and that's it. You know, this is so I'm trying to get the formula for this. Okay, the formula for this. The formula for this is going to be, this actually is a tangent vector. Okay, this is a tangent vector. Tangent to the surface, because look at this is gamma prime. So that will be n gamma is in that direction, n cross gamma prime, right? So this is because these two vectors are tangent to the surface at that particular point, because they're all perpendicular to n. Okay? But this can be expressed as, you know, we know that you already have, that's u double prime. I'm trying to express gamma 1. Gamma 1 is going to be gamma 1, 1, right? Delta u here is the u prime square. Gamma 1, 2, right? Gamma 1, 2, twice of 1, 2, u prime v prime. And gamma 2, 2, 1, here's v prime square and sigma u, right? Yeah. Right. So, yeah. So you can combine them. So 211 u prime square plus 2 gamma 212 u prime v prime gamma 22 v prime square sigma v. Okay. So I don't need to. This is my normal curvature. Okay. So this is a gamma. Okay. So now it's clear. The first part of kgn comes fine, right? The second part of kn. So what is my conclusion? It's easy to find out kn, right? And yeah, so from here, let's repeat again. This is the value of the second formula in the direction gamma. And the kj, how can I use kj? Kj is the dot product of this with n and e. Okay? So kj, this is geodesic curvature. The formula is going to be the coefficients u double prime. It's much more complicated. Okay, sigma u dot n plus gamma prime. Okay, and then v double prime. And that. Now, if you are able to calculate this, then that's no problem. I think it's computable. The reason is because we know how to find it, right? If you use a local coordinates, yeah, what is that? Okay, it's a cross product, right? And you can compute that because gamma prime is going to be sigma u prime and sigma v prime. Okay, and n is going to be sigma u cos sigma v, and then normalize it. Okay, so so basic, yeah, it's not too bad. Okay, so you can compute the number. You can compute this. Okay, and the dot product was the cross product, then dot product. Yeah, I'm not going. Yeah, so these have three vectors, so you can always calculate that part. Anyway, so this is a curvature, right? Yeah, this is a curvature. One can show that this is always perpendicular to this combination. This combination is always perpendicular to gamma prime, okay, the derivative. Anyway, so this is how do we find the curvature. Okay. So now, now I'm going to look at the vector field along the curve. Okay, let's see how do we find the derivative. Okay, so let gamma be a curve. I did not say it's unit speed. Okay, in a curve S. And the V vector field along S, okay, a tangent vector field. So that means V is going to be a function, okay? So V is a VT, is a function of a T which is V at the point gamma S, gamma T. Okay. So this is surface, and here's gamma T. At every point, gamma T, you have a tangent vector. But this tangent vector is a tangent vector to the surface. Okay. This is a V. Okay. So this depends on T, actually is a vector at the point gamma T. So you can locally express if there's a chart here, okay, a patch, okay, sigma. So at every point, right, the tangent plane is spanned by sigma U sigma V, right? So that's why you can always express it as linear combination of those two vectors. Oops. Okay, how can I do that, right? You know, gamma T can be expressed as U over T, V over T, right? If that is the case, then the vector field can be written in the form alpha T sigma U and the beta T sigma V. Right, because it can be a linear combination of those two vectors. Now, when you differentiate, okay, it's just as usual derivative. This is a vector in three-dimensional space. So this is not going to be in the tangent plane in general. So when you differentiate, okay, this is a vector, vector. When you differentiate, you may get something like that. So it's natural to get two parts. One is, this is normal vector, right? How can I project it back to the tangent plane? Okay. So here's the definition. Okay, the definition. The covalent derivative, right? Gamma prime is defined to be the projection of V prime onto the tangent plane. So we only consider this part, the projection. So then it's go back to, yeah. Then this is again is a tangent vector. Okay, in other words, this is going to be the tangent vector again. We only consider the tangent part. We don't care about the part, but the normal part, which is perpendicular to the tangent plane. So this is called covalent derivative. Derivative of V over T, okay, along gamma. Okay. So then you get, when on the surface, right, when you differentiate, although the surface is embedding a high dimensional space, but when you differentiate, you will you only consider the projection of the derivative into on the tangent plane. Okay, think about that. our universe, three-dimensional space, think about, right? It's embedded in maybe high-dimensional space. So you have a vector, right? A vector field in the three-dimensional space. But when you differentiate, you maybe end up with a vector, the derivative of the vector field along a path. Possibly is an object in high-dimensional space. But what you see is still the projection of this vector in the high-dimensional space onto three-dimensional universe. Okay. So then that's why when you differentiate, still get a new object, okay, in three-dimensional space. Here, so a vector field along the curving surface. Because this is a tangent vector field. Okay. So that's why I have a linear combination of these two, right? And then when you differentiate, you get another vector along the curve, okay? Another vector field along the curve. My question is, can we find the expression? I'm very curious about it. I found it but but how do you find the projection, right? Then when you find the projection, this is the formula. You subtract the normal part. You subtract the normal part. Right, so this is no longer be, this is always perpendicular to, nope, I don't have a derivative here, just gamma, okay? It's a notation. So, that's what it's called. So let me check. This is going to be 0. Okay. And it's easy to check that. Okay. Because NT is a normal vector, right? NT is a normal vector along the geodesic, along the curve, yeah, gamma T. It's a normal unit speed, yeah, it has a unit length. So that's why when you the dot product with this and the dot product with this is going to be 1. That's why the answer is 0. Okay. So anyway, this is indeed a tangent vector. Okay. This is how do we find the projection onto the plane perpendicular to the given vector. Okay. So basically just consider linear part. Okay, so if you differentiate, right, you have 2 parts. One is, and another one is a normal vector part, right? Okay. You decompose it into right? So this is a projection part, gamma, and this is the normal vector. All right, so if I can, this is tangent. Yeah, this is going to be tangent space. Tangent. All right, so if I find so we just go ahead and differentiate, then you get 2 parts, right? Then we're trying to find out the formula for this. So when I differentiate, what I'm going to do, I differentiate. Remember, Vt is going to be alpha T sigma U and the beta T sigma V, right? I just differentiate twice. Good. That is this is in the tangent space. Then I have to differentiate the second part. and then sigma VU, U prime, sigma VV, V prime, right? So we're almost done, okay? Now, what do we have to do here is there are some part is, some part is going to be perpendicular to the tangent plane, okay? So we have to figure out what is the UU, sigma VV, right? Okay. Then we ignore the normal part, which is perpendicular to the tangent plane. We have to go back to see how did we express sigma UU and sigma UV. So this is our formula here. Okay, this is our formula. Okay. And that's right. So let's recall our notation. Our notation is this. Okay, so I can express, yeah, let me go back to this formula. Okay, I needed to know, right? Sigma UU delta U squares 2 sigma UV delta U delta V, sigma VV delta V squared. And this is a gamma, right? Gamma 1, sigma U, gamma 2, sigma V, and plus the normal vector. Okay, so we don't need to worry about that part. What we needed to worry about is here, 1, 1, delta U squared, 1, 2, delta U, delta V, gamma 1, 2, 2, delta V squared, sigma U. Okay, so there's the additional part we don't need to worry about. Okay, so as you can see, sigma U is going to be gamma 1, 1, 1, sigma U, gamma 2, 1, 1, sigma V, and plus some part. This actually is L, okay? And the next part, sigma UV, is gamma 1, 1, 2, sigma U, gamma 2, 1, 2, sigma V. This is Lm from second fundamental form. And this is not the same N, Ln. All right, so now we go back to our formula. I think we do have, it's pretty complicated, right? We do have two parts. I want to express it. I consider, yeah, so what I got here, let me write down the formula, okay? Let me write down the formula. After I plug into the formula, so V prime T is going to be alpha prime T plus gamma 1, 1 U prime, gamma 1, 2 V prime, it's alpha T plus beta T. This is sigma U. Okay, and here's the beta T. Gamma 1, 1 U prime, gamma 2, 1 V prime. There's alpha T. And then, wow, the geometry is pretty complicated. So we have to use a maple samples, sigma V. And there's a part, I think there's a part we don't need to worry about. Okay? Because we only consider this tangent part. So this is a tangent part. Okay, this gave me actually these two parts. Okay, give me the gradient. The nebula, we call it nebula gamma. So I do have a formula here. Okay. So that is a formula for the derivative of vector field along the curve on the surface. Okay. So here's our definition. Okay. V over t is said to be parallel along gamma if the derivative is identically equal to 0. Exactly. Okay. So in the local coordinate, using the surface patch, and you get two systems of equation, two partial differential equation. Okay, so you see that, right? So this will be, each of them will be 0, and it's hard to solve it. So you get so you have something here, right? And something here, it's 0, right? I don't want to copy this. Okay, so that's a coefficient of 0. So you just needed to solve this system of first order differential equation, but the fully nonlinear order differential equation. Right, because inside, no, that's linear. Yeah, this is a linear. Because this depends on the, there's no alpha here, no alpha here in subclass. So those just a function of the t, right? Those just a function of the t. Depends on t, okay? Because gamma will, gamma, this for example, it's gamma 1, 1, right? Actually VT, right? And the gamma, when I just give you an example. Okay, it's a function of a t only. Right? It's a function of, Right? So you can, so what does that tell me? That tells me for any given cat, for any alpha 0 bit not, okay, there is a unique set of solutions alpha t, beta t, okay, satisfies the initial condition okay, right? And the solution linear depends on the initial vector. So this is the initial vector. Okay, this is the initial vector, right? So in other words, without using the surface patch, then we have the following still. Okay, for any vector we not okay, there is a unique Hello vector field Vt along gamma t satisfying the given, okay. And because the equations are linear, okay, so what you get is VT linearly depends on the initial value. Okay. Okay. That means if ever, it's always a linear combination. Okay. So if you have a, in other words, what does it mean? So if V0 equals lambda E1 mu E2, right? And E1 and the E1T, E2T are parallel, right? Along gamma with okay. Then you just use the same coefficient. Okay, is parallel along gamma with okay, with the initial value. That's called the linearly depends on the initial data. Okay. All right. So in other words, you have a vector, you have a gamma, that's a T1, right? That's maybe T1. So you have a vector field, parallel translated here. Okay. So this parallel translation, okay, is a linear map. Okay. So you get the map I, if this is a point P, and this is point Q gamma T1, then you have a map from TPS to TQS. Okay, it's defined as okay, and where P V is a parallel. Okay, along gamma. All right, so that's why along the gamma. So this is it's a parallel translation. Okay, so the factor here, we just mentioned this, we just proved that this is a linear map. Okay, not only linear map, I think it even preserve the length of the vector, but it's much harder to prove. Okay, it's a linear map, it preserves the length of the vector. Okay, and even preserves the angle between two vectors. Okay, but that's not easy to prove. Okay. It preserves the length of the vector, and we just see it's linear. Okay, the pair translation preserves the length of the curve, and all right, I'm going to take a look at an example because we don't do the example that we talked about. Here's an example. I consider a surface patch for the surface revolution. Okay. we assume that is always equal 1. So that means, what does it mean? So here's a picture. When V0, the y coordinate, it's in the x, y, xz plane. So we have a curve here, right? And this curve is gamma. And that is going to be f of u, 0, g and u, okay? This is it's a unit speed. Okay. And this curve, it's in xz plane. And if it's rotated along the x-axis, you get surface of a revolution. Okay, that's what we got. Okay. And I'm curious, we are going to look at the first fundamental form, second fundamental form, and the coefficients also. I'm not sure we have enough time. As you see, these equations for the parallel translation is independent. It only depends on the first fundamental form. Okay, because the coefficients here, gamma 1, gamma 1, 2, and those are only determined by the first fundamental. You don't need to worry about the second fundamental form. Okay. Yeah, gamma. So gamma 1, 1, gamma 1, 2. Those are the functions depends on EFG, the coefficients of first fundamental. It's nothing to do with second fundamental. Okay, it's nothing to do with how curved of the surface relative to the ambient space. Right? It only depends on the intrinsic metric. So it only depends on EFG. All right, so let's calculate this. I find out it's easy to check. Okay? We find out for this surface patch, okay, the first fundamental form can be written in the form, if you use a du square here, and fu square dv square. Okay. So IE equals 1, EF F is 0, G is fu square. Okay. So that's all we need. Okay. Then I'm going to have a list because I already have a formula. And let me find out. We needed to know the gamma, right? Gamma 1, 1. Okay, this is a formula already given in the book. Okay, you can solve it. So gamma 1, 1 is going to be, it's going to be, let's say, G EU minus 2F U plus F EV. Okay, 2 EF minus EG minus F squared. Okay, F squared, no square here. So I think they're all equal to 0, right? Because E is constant, F is 0, right? E is there, so it's 0. That's a 0. Okay. Gamma 1, 1, 2. G EV minus FGU. And twice of EG minus F squared. This is also equal to 0. because E is a constant, G, no, F is 0, that's also 0, just because F is 0. So gamma 2, 2, the 1, 2, 2, that's 2G, F of V, that's a 0, G and GU, minus F of GV, that's a 0, EG minus F squared. Okay. So what term is not equal to 0? I think F is 0, F is 0, only the term in the middle. It's twice of, right? F squared, then I think it's F cubed. Okay. And the denominator is product with 2F squared. So the answer would be negative F, Fu. Okay. So most of the coefficients are all 0. Okay. Then let's finish the other part. At the same time, I write down the formula, right? Okay, so which one is now going to be 0? I think they all should be 0 because E is constant, F is 0, F is constant. So F is constant, that's 0. And that's E, yeah. F is 0, so that's right 0. Gamma 2, 1, 2, EGU. I think this is okay now. We're almost there, okay? So E is 1, EGU equals twice of FU, right? The second part is 0, here's 2 F squared. So my answer is FUF. I gamma 2, 2, I think this is going to be 0. So all of them is 0 except for 2, okay? Except for gamma 1, 2, 2, okay? So gamma 1, 2, 2 is going to be negative FFU, and the rest of them is the rest of them all 0, okay? All right, so now we come to the equation. Okay, so this is going to be 0 if and only if I think this V is a vector, arbitrary vector field, right? Okay, I just want to determine those coefficients. Okay, it's satisfying the following equation plus gamma 1, 1 U prime, right? And gamma 1, 2 V prime alpha plus gamma 1, 2 gamma 1, 2, 2 V prime and the beta. Okay, this is supposed to be 0. Let me simplify this one first. What are the, so this is 0, right? Only the last term is not 0. And this is a 0. Okay, among the coefficients. Yeah, so this is a minus FFU V prime beta is 0. Okay, so that's the first equation. It's pretty simple to study. Okay, then we look at the equation for the beta. All right, so we only have this term is now going to be 0, right? Gamma 2, 1, 2. So this gamma 2, 1, 2. Okay, and the rest of them will be 0. So it's gamma prime and 2 and 2. So that's FU F and FU F U prime beta. Okay, so the parallel vector fields along any curve will be completely determined by these two equations. Okay. Fine. And this is our surface, right? This is our surface. This is our surface. Okay, we're talking about given arbitrary curve gamma. Gamma t is going to be alpha, u prime t, v prime ut and vt. Okay, so ut vt's are here. Okay, so the curve is fixed, and so the vector field is going to be alpha t sigma u, right? And blah blah, there's something, and beta t sigma v around the curve. So those coefficients are determined by this. This is about, yeah, this is a v. It's not u. Okay. But I think it's not easy to solve it, right? Can you solve it? No. But there's some special I just want to look at this curve, the special curve, any curve around this, and maybe it looks much simpler, the parallel vector. So look at the gamma t, and this is going to be fixed v, right? So I think the v here is going to be constant. The vt is a v now, okay? Ut will be just t, how about like that, right? Then I'm going to plug into the bar formula, then a vector field along the curve. How does that look like? Okay, so the, along this curve, I'm going to talk about, I'm going to look at how do I determine the parallel vector field. All right, so I got about 3 questions. Okay, alpha prime plus or minus FFU. However, V prime is going to be 0. So that is going to be 0. V prime is 0. So beta prime plus FU F. U prime is 1. So V prime is 0. So that's it. Okay. It is much simpler. Okay. So you look at this equation, alpha prime t is going to be 0. So alpha t is going to be constant. Okay. So we determine alpha. Now how do I determine the beta? Beta, see, this is a FU, right? And U is just a T. Yeah, F prime T, right? Here's T. So I can solve it. Okay, it's easy to solve it. You divide by, right, by beta on both sides. Then this is the natural log of beta t prime, right? Plus natural log of f. Okay, but then I combine them. Right? So that means beta t, f of t must be a constant. And let's call the C. Okay, I get the formula. This is just C over f of t. Okay. So that means, okay, a parallel vector field must be in the form. Okay. So parallel vector field okay, along gamma t, which is already given sigma and the t and right? Okay. And if we want to put more details here, it's f of t cosine v0, f of t sine v0, and the g of t. Okay. And then are given by okay. What is my alpha? Right, alpha is constant. Okay. And my beta must be C of f of t, something like that, sigma b. And that's it. So you completely determine the parallel vector fields along the curve from top to the bottom on this kind of surface of a regulation. And this kind of exercise, and in general, is very complicated when you do computation. You see, you have to determine all the coefficients, gamma 1, 1, 1, gamma 1, 2, 1, and total how many? 6. Okay. But